Alrighty, everybody, this is the introduction to Chapter 4 in Honors Chemistry, the arrangements of electrons and atoms. And you'll see that for the background, I was very purposeful and chose some fireworks. And you'll see what that has to do with it as we go through these videos. Okay, so just as in the other chapters, we are going to do a little bit of a pretest. So please get a piece of paper. I promise you, it makes it all that much better. And you're going to draw each one of these scientists' model for the atom. Okay, they're in chronological order. So I want you to write down Democritus, then Dalton, then Thomson, then Rutherford, and see what we remember from the previous chapter. Okay, you can draw out the model, label things if you have to, and see how they differ. Okay, in class I'll collect it and then give it back to you at the end of the chapter and we'll see what you remember. Okay, so what we're going to do now is walk through history. Okay, just like we did in the previous chapter, we're going to see how these models evolved over time. So what you should have done first is Democritus. Okay, Democritus is this guy from like 342 AD, the Greek philosopher. He's the one that came up with the thought experiment saying that everything breaks down into an indivisible little particle, atomos, and that's what we have for him. Okay, next we have the father of chemistry, John Dalton, who's this fellow right here. He came up with Dalton's atomic theory, and that atomic theory is going to describe how atoms are indestructible and there are no subatomic particles. Okay, third, you should have drawn for J.J. Thomson the plum pudding model, which is what I call the mint chocolate chip ice cream model, which is basically going to be your electrons scattered throughout positively charged matter. There's positive matter, no protons yet, okay? But there are electrons randomly strewn all about, just like the chocolate chips are random in our mint chocolate chip and the plums are in the plum pudding. Okay, fourth was Ernest Rutherford, and he had the famous gold foil experiment, and that gold foil is where he shot those radioactive alpha particles, as we also learned from our radioactivity chapter, nuclear chapter, the helium atoms. And he's going to shoot them at the gold foil. Most non-deflect, they go straight through, but every so often there is a very, very, very succinct deflection, and that deflection is going to mean that there is a dense, positively charged nucleus. So this is the discovery of the nucleus. Okay, so with that little bit of a review is where we leave off in history, and the newest information for this chapter, things that we haven't gone over yet, is going to be the work with Niels Bohr. Okay, Bohr is actually a scientist that worked with Einstein, and he found that the electrons had some order to them as well. Okay, and the whole point of the chapter is to talk about how the electrons are arranged. Okay, so he called them orbitals. Okay, this is when the planetary model really came out of the solar system, and we had our sun in the center and our planets that revolve around them. And this is probably what you recognize the most as a common model of the atom. Okay, it's not, orbiting with, gum, but it's orbiting those electrons around in distinct paths. So I was a track runner and a track coach, so I always like to think of lanes of a track. Okay, so stay in your lane, girl, stay in your lane. Okay, the energy levels are these regions of space around the nucleus where the electron is most likely to be found. Okay, so what Bohr did is he ended up working with hydrogen. Okay, hydrogen is the atomic number of 1. So that means it has 1 proton in the nucleus, and it means it has 1 electron. So that 1 electron, he was able to look at the different emission, which means the different energy signatures, which is what the spectrum is, and we'll get to that at the end of the chapter, of how they jump in between these different levels. All right, and it worked great for 1 electron. Okay, later on scientists are like, this isn't exactly true for what we have, but it is something that was really groundbreaking, all right, these energy levels. Now, if you know anything about track, you know that the lengths of the track lanes are not equal. So if this is the football field in the center and this is lane 1, 2, 3, 4, when they do the 400, which is 1 lap around the track, they have to do a stagger start. And the reason why they have to do a staggered start is because you have to run the same distance. So somebody will start here in one of the lanes, the next person will start here, next person start here, next person start here, and they'll run to the finish line. So that way they run an equal amount because each of these energy levels has different energy. Okay, so it takes the most energy on the outermost orbital, and it's going to take the least amount of energy on the inside. All right, so the next scientist that was really working with our model, you might remember from Breaking Bad, and it is a very purposeful name, and that is Heisenberg. Okay, Heisenberg had an uncertainty principle that is applied to the behavior of matter, especially to these electrons. So when watching the show, and Walter White's character renamed um, his ego as Heisenberg, I start cracking up. And my husband's like, what are you talking about? He's not a scientist. And I was like, Heisenberg, it's very well calculated. It means that he both exists and both doesn't exist. And you are going to kind of find it impossible to figure out the position and the speed or velocity of any particle. So, like, you can't really find out where he is because he doesn't really have a predictable pattern. Okay, so when Heisenberg might have or might have not been here, I start cracking up because I'm getting all the science references. And my husband's like, yeah, I don't really get that. But it's very similar to what you would think of with like ripples in a pool. Okay, so all the ripples that you get when you put like a pebble into a pool and how they make all the different waves. But if you were to add a second pebble, those waves start to overlap and they start to bend. So there's some diffraction and there is some interference. So it's very difficult to predict exactly where these electrons, where these particles are going to be. And with the work of Heisenberg, which hopefully you don't go through life applying everything to Heisenberg because you would never make a decision. There was another scientist that worked with Bohr, with Einstein. All these scientists worked together, which is like really incredible. And oh, what a time to be alive. And that is by the name of Erwin Schrdinger. And Schrodinger, you might know him for his feline fetish. That is the scientist that is accredited with the current model of the atom, the quantum mechanical model. So this is the current model. You'll see me abbreviate it QMM. And what we're looking at here is looking at the probability of finding an electron in a region of space. Okay, so somewhere within an orbital. All right, and this was developed with Schrödinger's equation in 1926. It's all based on the probability of being able to be located somewhere in the atom. Okay, and that's what we're going to use for our current model. Okay, Schrödinger's experiment basically had a box, there was a cat inside, and there was some poison. And it was a soundproof box, and they said, is the cat alive or is the cat dead? And everyone in class debated over it. Well, it's obviously dead. Really? How do you know? Well, it's definitely alive. Really? How do you know? And through math and through lots and lots and lots of calculus, they found that both outcomes were possible simultaneously. All right, until you open the box and one of them is determined to be true. So this is what people in the sci-fi community call parallel universes, like which one is true, what's going to happen. Well, both can happen until one is chosen and the other one stops. So it's like worrying about, how did you do on a test? Well, you could have, done really good on it or you could have done really bad on it. And you're not really sure which way it's going to go. So until you know, both are true simultaneously. So that quantum mechanical model leads to finding these areas of probability and these very complicated shapes, which we'll show you in the next video, and where our electrons are going to be.